Myself, Dr. Shubhankar Sen, Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, will be offering the 12-week NPTEL theory course, Finite Element Method in Thermal Engineering, during the January to April 2026 semester. The finite element method is a highly accurate discretization or numerical integration technique that owns several advantages over the other competing methods, such as the finite difference and finite volume methods. The flexibility in choosing elements of different shapes to handle complex geometry problems without resorting to coordinate transformation, easy implementation on structured, unstructured, orthogonal, non-orthogonal meshes, as in implementing the flux or natural boundary conditions, ability to preserve the symmetry enforced via the Laplacian operator irrespective of the boundary condition or element type, render the finite element method as a versatile numerical tool for handling complex thermofluid problems. The prime goal of this NPTEL course is to acquaint the students with detailed concepts and implementation of a robust numerical tool to thermofluids that has otherwise been employed mostly for solid mechanics problems. This will be performed via step-by-step derivations, simple and lucid explanations, and also with the aid of sufficient number of supporting figures and numerical problems that will clearly illustrate various implementation issues with clarity. Some background of linear algebra, differential and integral calculus, fluid mechanics, and heat transfer are adequate for attending this course. The coding skill will be an added advantage. I believe that after this course, the students will be confident and clear about the basics of finite elements in heat transfer and fluid flow in single and multi dimensions. This course is highly recommended for undergraduate, postgraduate students, PhD scholars, postdoctoral fellows, faculty members, industry personnel and research personnel working in various labs, participants from mechanical, aerospace, civil, chemical, petroleum, environmental, ocean engineering, applied mechanics, computer science, mathematics, physics, or other relevant departments are welcome to attend this course. Students and researchers working on COMSOL multiphysics or other FEM packages will be benefited from this course. The participants with exposure to computational fluid dynamics or CFD will find this course particularly useful. The course content is unique and differs significantly from those covered in a standard text on the finite element method. The course will begin with introduction to tensors and a review of matrix properties. This will be followed by the coverage of basic variational methods and a brief review of governing equations pertaining to thermofluids. Subsequently, the integral theorems and different arrays for generation of mesh, global equation numbers, and assembly of element level matrices and vectors will be covered. Generation of single and multi-block structured mesh will be illustrated along with array generation for simple and coarse unstructured meshes. For heat transfer and flow problems, each a generic form of the algebraic equation will be presented that will contain contributions from the source terms as well as boundary conditions. The implementation of essential, natural, and convective boundary conditions will be illustrated in 1 and 2 dimensions with adequate examples. A major contribution of this course will be a clear demonstration of the difference of the finite volume and finite element methods relative to an elliptic partial differential equation. Eventually, solutions of an elliptic PDE in 1 dimension obtained using the finite difference, finite volume, and finite element methods subject to essential, natural, and convective boundary conditions will be compared. Finite element solution of an elliptic PDE in 1 dimension will be solved using linear and quadratic bar elements. The heat transfer problems will be solved in 1 and 2 dimensions with linear triangular and bilinear quadrilateral elements for 2-dimensional problems. Implementation of Gauss quadrature will be demonstrated for an arbitrary shaped bilinear quadrilateral element. Various time integration schemes will be shown in conjunction with parabolic and hyperbolic PDEs. The implementation of implicit, explicit, and Crank-Nicholson schemes will be demonstrated via numerical examples showing oscillation-free or stable and oscillatory solutions. Under transient transport, the case of first order wave equation, which is a hyperbolic PDE, will also be covered along with numerical examples. The one-dimensional steady and unsteady convection diffusion problems will be handled next, where numerical examples involving linear and quadratic elements will be illustrated. The inability of Gauss-Seidel iterative solver to yield solutions in a non-diagonally dominant matrix will also be covered. The concept of stabilization of the convection term will be demonstrated relative to the one-dimensional convection diffusion equation. Finally, Galerkin and Petrov-Galerkin formulations of the Navier-Stokes equations of motion will be demonstrated in 2 dimensions. Thank you very much.